So this is a Verilog file of our project. At the beginning, it's a declaration of this modulo with its name RLE-ENC, and the input and output signals, the clock, reset signal, read request, receive ready input data, output data. And the first declares the input and output signals, like the clock signal, reset signal, 8 bits input data, and 24 bits output data. And this part defines the some registers with its appropriate size, like the 23 bits bit count, 4 bits shift count, 8 bits shift buffer. And the parameters that defines the values of each state. The 4 here means it's 4 bits and in size, and the B here means in binary, so this is 4 zeros and this is 001. The always means it will running forever, and this part describes the relation between each state. It gives the condition that one state will goes to the next state, and the always here. The second part describes the specification of each state, like what kind of function and what kind of action this state will do. So one case is the init states. The next state will be requested the input, and when we request the input, if we already receive the data, so our next state will be wait for the input. Or else, if it's the end of stream and the bit count is not equal to 0, the next bits will be count down. That means we finished the counting, and else the next state will be just request the input back to itself and wait for the receive ready signal. And there's with also have with input read input account bits. In the shift bits, when the new bit string is set to 1, that means there is a bits change from 0 to 1 or 1 to 0. The next state will be count down. If it's not a new bit stream, the next state will be count bits, and the countdown is send the output, the data to the output, and with output reset the count. If it's the end of stream, we'll reset the back to the init condition, and if not the end of stream, we just continue counting the bits. And here in the init state, we set all the bit count, shift buffer, read register, write register, all to and the shift count all to 0, and set the new bit stream, because this is the beginning is initial, so there's a new bit stream, so the new bit stream set to 1. In state request input, we set the read register equal to 1 to, and we assign the read register and write register with the read request and the write request signals together. So by changing the read request, we can control register. We can control the request signals. So because it's a request input, so the read register set to 1, and the shift count will set to 0. Let's reset the shift count. And in the wait input, our read register will be set to 0. And in the read input, we will, we use a non-block assignment to gives the input data into the shift buffer.
Okay, so in count bits, we want to increment the count by 1 if it's the same, if the bits are the same, and we want to reset the count if the bits are different. So in this case, if new bit stream just indicates whether there is a different bit if there's a change. So we just reset that variable, and then we want to store the new value. So if it's a transition from a 0 to a 1, we want to store the 1. Or if there is a transition from a 1 to a 0, we want to store the 0. And then we reset the count and we increment by 1. In this else case, first, if the values are the same, then we want to just increment the bit count. And then else, this is when the bits aren't the bits change. So we want to set the new bit stream variable to 1, which then like just jumps back to this case, and it will notify that there is a change, and then reset the counter. And then in shift bits, we just shift the shift buffer to the right and then increment the shift count, which means that we just like go through the bits of the input. And in here, in this diagram, it shows that the count bits and the shift bits, they're looping, and this just means that the shift bits will go through all the input bits, and then it will count until it goes through all of the input bits. Then when it goes through all of the input bits, it will go to countdown, which just notifies that it is ready to write, and we just indicate that by writing a 1 to the writing register. And here it just waits until the output is fully written, and then we just reset the count, indicating that there's that we're done. Here are a bunch of assigns that just assigns that read register sends a signal to read request, and then same with write request. And here is basically what it says in this slide. The 23rd bit is basically the value, and the rest of it is how many times it appears.
Hi, I am doing the job for the test branch, so here's my code. I first set up the timescale from 100 ps to the 10 ps, then we module another modulism in the module sim that we do the reveal of the test branch. And like what we did in the Verilog file, we first create a clock and reset test branch for the register, same as the ready test and the receive test branch and the send test branch. Then we sending the 7 segments to the data so it can be sending out and sending in. Then we also have a register for the end of stream so that we can send an intercept to stop this kind of process. Then we write up our 23 bits to our data register, so that is total of 24 bits, but it can be count to 0 to 24. Then we wire it up to the register of the reading and writing. Same for the institution of the circle of those on the test. Then what I did, we start to try to make the clock running forever. We first initial that is set to be 0 and let it end so that no progress is in the CPU. And then we start to reset for a few cycles. We first set the receive and sending to 1 cycle to see if the end of the stream can be 0. After that, we can start the whole progress to do the test branch. Like what I write here, we first did a totally 0, and to see if there's a receive test branch from the data master. Then we did another total of 1 to see if this can be sending back. A little bit change of the code here. Same as what I did here, like the first 7 segments, the first 7 bits is 0 and the last one is 1. to see if they're coming back. And then there's this test. The first one is 1 and the remaining for the 0. And another one, like what we did, it doesn't mention the lab report, but we want to see if that works. So it's 10101010, and to see if that will stop, because it's causing a receiving of the data to be right, and that will end the process. After that, we can run on the model sim, but it took like a little bit time to run, so we made several screenshots. Here's what we did here. First is the like what we did here is first 7 bits is 0 and the last one is 1, and it looks good. Like first 7 bits is 0 and last one is 1. Then there's a first 7 segment is 1 and remaining, and the last bit is 0. So that is this progress. A little bit mess in the front part, but after that everything looks good. Then we want to see like if everything is 0, everything is 1, that works. So here's everything is 1, and that looks perfect, I think. After that, we need to make it congruent to the two data 1, data 2, everything is 0, for expect the last one is 1, and everything is 0. So that's the combination of the conjunction of two data in this progress. So this is a progress what I see, and it's running, looks good. After that, we combine all the pictures what we had before and made it in overall diagrams. So this is overall diagrams, and it follows like the clock flows to the interrupt. So yeah, I think the test branch works fine, right? That's the end of the demo. Thank you.
Hello, so this video is for ECE-332 Embedded Systems 2, and we're going to do the demo of Lab3, which is modeling Simulink. So first we have the Verilog file right here and the test bench that we wrote. By now you should understand both of these files, and we're gonna model them using ModelSim. So first we import in the two Verilog files, and then we need to compile each of these. We know that was successful because it said so, or else the status will be at X right here. Now we go to library, all the way down to work, and then we modeled, and then we simulate the test bench. Here it goes. So these are all the objects, which is like the registers and the input outputs. So we want to model that into the waveform. What we have to do is click on all of these. Well, you can click on whatever you want to show, but for now we're just going to click all of these, and then we're going to run it. Now here's the run button, but this is the run length. So right now we have these test cases with, so these are the test cases with the 8-bit length right here. I'm not sure if the 10 nanoseconds run length is enough, so we're going to run the first 10 nanoseconds. And then as you can see, that gets, the first one is all zeros, and then that gets to all ones. So that'll be the first two tests, and then we have to keep on running again to get to the last three here. So if we just hit run again, it'll be 1 0 0 0, so 1 and 7 0, so it'll be right here. So we need to run one more time. No, let's see. One more time. All right, there we go. So first we import in the first input data, which is all zeros. We need to test that, so the in data right here is all zeros, and it started with, this is the 24-bit that is the output that needs to be ran. So the first bit should be the ID bit, and it should count to 1. So your ID is 0, and then it count 1, and then it should go up to the the answer should be 8 bits. So if you just, oh yeah, this read is a 1 because you're reading in the data, and then after you get an answer, you just see that the out or the write register should be a 1 to write out the answer. So if we could count 1, 2, 3, 4, 5, 6, 7, 8. All right, there we go. It's 8, 0 for the ID bit, and 8 for the consecutive numbers of zeros. And then we read in the way to read in the data, which is why it's a 1. Now the read in data is all 8 ones or all ones. And you can see right here that it writes out the previous one, so it's the ID bit of 0 and the length of 8 that gets written out, and now we need to count for the new input data, which is 8 ones. Now that goes to, now you see that the ID bit is 1 and the count is 0, so if we go count 1, 2, 3, 4, 5, 6, 7, 8. Now it just reads in the input data, which is now is 7 zeros and 1s, but afterwards you should see that the write register is a 1 because we need to write the answer for the previous one, which is 8 zeros. Wait, which is 8 ones. Which is 8 ones, and then that gets continued to this bit right here, which is the rightmost one, so that 8 should be a 9, which is shows right here, and then afterwards there's a write for the write output data. So that gets continued, so that gets a reset of 0, and that gets 0. And that will be the test case for the first 2 leading into 3. I'm not going to go do all these test cases, but I'm just going to move towards the end and go to the consecutive 1, 0, 1, 0, 1, 0, which is the worst case scenario for our compression algorithm. So if I just move all the way to the end, here we go. The input data is 1, 0, 1, 0, 1, 0. And then we just, let's see. Well, we could start off anywhere, but let's start off right here, right? So now you read in the data. So it starts off as a count to 0 first, and then now you write it, count to 1, write it, count to 0, and you write it, and then count to 1, and then you write it. So that goes back and forth. You can see that with the write register waveform that has more occurrences than the previous test cases. So that is our, test cases demos. Now, just a short note, we could go back to the timing. This is something that I thought was pretty cool. So you can see that from between the transition from all zeros to all ones, that happens at 5,500 picoseconds. Let's see, 5,500 picoseconds, because you set the time period to be 100 picoseconds, and 100 times the 50, the one that you waited for the input data, and then you have to wait 400 picoseconds for the receive ready registers, and then your next 50 picoseconds for the next input data. So that adds up to 5,500 picoseconds. And as you can see right here, this is the start of receiving the data of all ones. So that shows that our Vertilog file is accurate. And thank you.